Okay, so back here, the second part of circulation, we left off the last video with the idea that as we're going to rely more and more heavily on our lungs for respiration, we're going to take advantage of oxygen-rich air and try to become as efficient as we possibly can with oxygen delivery. With this guy, right, our happy little lungfish, one of the things we saw with his or her plan to ventilate using a lung was that because of the single pathway through the heart, that oxygen-rich blood always got mixed with deoxygenated blood. And so it wasn't as efficient as it possibly could be, which diminished the power of using a lung as a respiratory membrane. So as we become more and more reliant on lungs and less reliant on gills, to the point where we're no longer relying on them at all, we're going to see an evolution of the heart getting away from that linear pattern and getting more into kind of the pattern we saw at the last slide of last video, where we have two separate loops, a right side and a left side, that are dealing with different blood sources and oftentimes different blood destinations. So here, again at the top, just to kind of as a reminder, a fish heart, again, was linear, right? We enter a sinus venosus, we enter an atrium, we enter a ventricle, we leave via a conus arteriosus or a bulbus arteriosus and pass on our way. With amphibians, we're going to start adding chambers, okay? So we're going to still have a single ventricle, and we're still going to have a conus arteriosus. In this case, it's the same thing as the bulbus, just slightly different. There's still going to be a sinus venosus, right? But we're going to add a left and a right atrium. We're going to add a receiving chamber for a right circuit and a left circuit, okay? And so blood is going to come back from the lungs to the left side, and blood is going to come back from the body from the right side. And they're both going to enter the same ventricle, okay? Which you would think, okay, this is not great. Right, this is not, obviously, we've gone ahead and we've just taken these two separate sources of blood and now we've just mixed them right back up again. What the hell? Well, as it turns out, if you look at the myocardium here of the ventricle, there's these little ridges in here called trabeculae. And these little trabeculae kind of have the effect of subdividing different little chambers of the heart, okay? And because oxygenated blood and deoxygenated blood have different tensions, okay? They naturally don't mix and mingle very well. And so if you can provide them separate places, like oil and vinegar a little bit, right? Or oil and water. If you permit them to segregate, they will. And so they segregate themselves within these little trabeculae, these little grooves here separated by the trabeculae. And so when the ventricle contracts, the deoxygenated blood leaves the heart, right, and passes through one of our little arches here off to the lungs, to the skin, okay? And the oxygenated blood actually passes off to the systemic parts of the body, going out to the tissues of the body. So it's not perfectly efficient, kind of like their means of ventilation is not perfectly efficient, right? We talked about stale air and fresh air mixing in that gular sac there, but it's better than nothing, right? It actually is surprisingly efficient as far as that goes. As we become, again, more and more land living, we get away from amphibian lifestyles and onto purely terrestrial lifestyles with lizards and turtles and things like that. We get into a situation where we still have a left and a right atrium. We still have a single ventricle, okay? But instead of having those trabeculae, we actually subdivide the ventricle up into three largely distinct chambers. We'll call them a cavum venosum, a cavum pulmonale, and a cavum arteriosum. I'm not overly worried about you remembering that. Okay, that's if you've already taken comparative anatomy, you already know this, hopefully. Hope you remember it. If you haven't taken comparative anatomy yet, you'll learn it. But the idea here is that like with those trabeculae, okay, our different cavae, right, or cavae, are means of separating out blood by destination, okay? So the cavum arteriosum, the blood that sits in the cavum arteriosum, ends up going out to the body, okay? The cavum venosum passes blood to the cavum pulmonale, which passes blood to the lung, okay? But again, it's a means of working with a single chamber, but still having a way to kind of maintain separation of circuits. Again, it ain't perfect, right? We do get some intermingling of blood, some deoxygenated blood goes out to the body, some oxygenated blood goes to the lungs. It happens, okay? But it's more efficient than what we saw with the amphibian heart, which was in turn infinitely more efficient than what we saw with the lungfish heart. So again, it's stepwise progressions. That's how evolution works. It's not miracles happening left and right. It's kind of small miracles happening a little bit at a time. When we get into crocodile hearts, some pretty remarkable stuff happens here. We have essentially, functionally, a four-chambered heart with a left and a right ventricle, and a left and a right atrium. And this is going to be true of all archosaurs, so crocodiles, birds, dinosaurs, all those guys, similar to the way that the four-chambered heart works in mammal. With crocodiles, though, they have one additional special little thing. And if you know anything about crocodiles or alligators or caimans or gharials or any of those guys, you know they spend a lot of time underwater, right? They spend a lot of time diving. And so because they have a large venous reserve, right, like we saw in the last unit, they don't, as long as they're resting, right, they don't necessarily need to send blood to the lungs at all. If they're diving, there's no point, right? They're not exchanging really any gas with the air, so all they would be doing is actually taking oxygen from the blood and putting it into the lungs. So what they're going to have is a little shunt, okay? If I can find my pen here again. Shunt. Be very careful saying this in public. So it's a shunt. And all a shunt is basically where we can divert flow from one pathway to the next. And that pathway is called the foramen of Panizza. And it is between, so they have a weird circulation pattern. Again, if you come in and learn, you take comparative anatomy with me in the fall, if you haven't taken it, please take it. It's a fun course. I like to think we have fun. We'll talk about all these different little blood vessels coming out of the ventricle. But the idea here is that they have basically, again, two pathways. They have a pathway that goes to the lungs, and they have a pathway that goes to the body. And the foramen of Panizza connects those two pathways. Okay, and so when it's open, okay, when they are breathing air, right, they have a normal circulation where blood goes to the lungs and comes back to the heart and out to the body and the lungs and on and on and on, right? But when they're diving or holding their breath, the blood that would normally pass through here, right, and go off to the lung, gets closed off and gets sent to the body instead. So they can use up that venous reserve, okay, and not have to return to the surface. It enables them to stay down significantly longer. And again, that's the foramen of Panizza. For mammals, you know, again, you've seen a mammal heart before, I hope at some point in your life. Right and left side, right atrium, right ventricle, left ventricle, completely separated all the way down. The same is true for birds. Bird heart works very much the same way a mammal heart works. And so we have those two completely separate circuits. We don't have a situation like this where we can shunt blood from pulmonary to systemic and pulmonary to systemic. They're completely separate their entire way. Okay, right side always receives deoxygenated blood, left side always receives oxygenated blood. The way it works in all vertebrates that have right and left sides. So kind of to sum up vertebrate life then, right, in terms of pathways, we go from something very simple, right, something in series like a fish, to as we add additional structures to it, right? So say we add a lung, right? Say with a mammal or a bird heart, which are identical, essentially. We end up with multiple pathways, multiple different loops, multiple different circuits, pulmonary, systemic, okay? And the degree to which these two are separated, right, depends on the separation, the internal separation within the heart, right? So we get something like a turtle or a lizard or even an amphibian that have imperfectly or incompletely separated ventricles, there's going to be some mixing and mingling, right? It's not perfect, but it's better than nothing, right? We get a little more efficient as we go from amphibians to reptiles. The other thing that we see here with reptiles differ from amphibians is, of course, amphibians use cutaneous respiration a lot. Amniotes, so exclusively terrestrial, so non-amphibian tetrapods don't really. So they lose that capacity. Then, of course, with our crocodilians, we have this shunt, this foramen of Panizza here. It gives us a little more flexibility. Okay, so that's kind of the normal stuff, right? The expected stuff. Once we get out of this realm, though, get out of the realm of vertebrates, things get wacky in a hurry. So we're going to start here with octopodes, octopus, okay? And right off the bat, we're going to start doing something very different, and we're going to add some hearts, okay? So there is a normal systemic heart, right, that we would expect, okay, that pumps blood out to the body, right? But the systemic heart, unlike the systemic heart of fish, is behind the gills, right? So blood passes through the gills first before it gets to that systemic heart. So we need to have a means of generating pressure to get blood across the gills in the first place. And so there is a right and a left branchial heart in an octopus. Branchial here meaning of the gills. And so a branchial heart simply sits right before the gill and provides pressure to get blood across the gill. So we can get it to the systemic heart where it pumps it out to the body. Very, very unique system for us. Once we get into arthropods, so insects, spiders, crustaceans, those kinds of things, again, we get pretty wacky in a pretty big hurry. One of the ways that we're going to get wacky in a hurry is that we're going to lose most, if not all, blood vessels. Okay, there are going to be some large arteries. You can see them here. Okay, leaving the heart. But if we skip ahead here for a second, once blood kind of leaves those arteries, they just end, right? And the fluid within those vessels then is just kind of dumped out into the body, all right? And if there's no vein, right, if there's no returning mechanism to come back to the heart, how do we get blood back to the heart? Well, we do so through these little holes here called ostia. A singular one here is ostium. And they're literally just valves or flaps, right, that as the heart expands, it sucks fluid. We can't call it blood, but it sucks fluid into the heart so that when it contracts, it can push it out the arteries. So if we're not calling it blood, because there are no blood vessels, we have to come up with a different term for it. So we're going to call it hemolymph. Okay. So in arthropods, right? Again, term if you're not familiar with it, arthropods. So crustaceans, insects, spiders, all those guys, things with an exoskeleton. They have hemolymph. So the vast majority of animals on the planet, by number, by diversity, by biomass, whatever measure you want to measure it by, have no real blood vessels, have no blood. They have hemolymph instead. And indeed, a lot of these guys have hemocyanin, chlorocrurin, okay, non-hemoglobin type pigments in that fluid as well. So it's a very, very interesting, unique system. So if we look at the circulation pattern, then here we've got a crawfish, just for grins, I guess. Coming out of the heart, right, we have a couple of main distributing vessels here, these arteries, but blood just kind of, hemolymph, I keep catching myself, hemolymph just kind of fills the body cavity, right? And kind of sloshes around outside of all of the organs and things like that. It is not an efficient system, right? Again, another big reason that we don't see giant insects and giant crayfish and all these other giant massive things. They're just really kind of shitty at delivering oxygen to their tissues because they don't have blood vessels. Why don't they have blood vessels? They just don't. there's not a good reason behind it, just how they happen to evolve. And so with that in mind, then thinking about kind of where we might expect vectors of flow to occur, right? This is what we would expect to find in terms of flow patterns within, say, an insect here. Again, directed within those hearts, directed within those arteries, but as soon as we leave those vessels, it's just kind of a free-for-all. Now there is some, and this is the last thing we'll talk about, there is some means of controlling where things go. So while they don't have blood vessels, if we look at the inside of the tissues, we look at a cross-section of the tissues, we find that it's not just one big hollow lump. There are oftentimes trabeculae within these tissues that subdivide out little chambers, okay? Little pools, little places to kind of canalize the flow of blood. It's not a blood vessel, right? But it's kind of getting around the same idea, and these are called lacunae. Pull my pointer back up here, called lacunae. And so they do get this hemolymph flow. And again, the blood is not the right term here, hemolymph. But to try to get this to flow in a very specific place, right? Even though we don't have a vessel directing it there, we have means of kind of channeling it where we need to go. And if we look at where, say, the muscle fibers are within this tissue, a lot of these little lacunae correspond to places where there's a lot of oxygen demanding tissues. Okay, all right. So that's good for that chapter. It's very condensed, obviously, from where we normally would go, but lowered expectations, right? Here we are with that. So we'll close this off, and then in the next set of videos, we'll talk about the next chapter.